All right, this is lesson 3.1 for our calculus class. The new unit, we're working with implicit differentiation and inverse differentiation. So the first lesson is called implicit differentiation. What we're going to learn in this lesson is how to differentiate an equation that cannot be solved for y. So up to this point, we've only differentiated functions, which are equations that can be solved for y. So how do we do that? And the next thing we're going to learn gives away the answer to the first one. What is implicit differentiation? So let's take a look. Okay, so here's a function that's not solved for y. Now, this particular function we could solve for y and differentiate, and we know how to do those things right now. We could just subtract 2x from both sides, divide both sides by 3, and then there we'd have y. We could use power rule to differentiate from there. And so now, but what I want to do is I want to show you how to solve this using implicit differentiation. And so let's show the necessity of that. So how about this one right here? This equation, x squared plus y squared equals 25. So we can't really solve for y on this one, or if we do, it's not a function that we can work with or differentiate, because well, if we take the square root of both sides, then we get y equals plus or minus the square root of 25 minus x squared. And because of that plus or minus symbol, that makes this not a function. If we graph this equation, we know that it's the graph of a circle with a radius of 5, because x squared plus y squared equals the radius squared. That's an equation for a circle. And so how do we differentiate this thing? Well, we're going to use implicit differentiation to do that. And so how that's different from before. Before, when we find the derivative, we could just plug in an x value and find the slope of the tangent line on that point of the graph. Well, now if I give you an x value, let's say the x value is 3. Well, at x equals 3, we have two y values that we can go to. We can go to 3, 4. 3, 4 would be on the graph of the circle. Or we think of 3 squared plus 4 squared would be 9 plus 16 would be 25. We can also confirm 3, 4 is on the graph because that's a right triangle. 3, 4, 5. The radius is 5. Anyways, so if x equals 3, we could be at 3, 4, or we could be at 3, negative 4. So we can't really know, using the way we know derivatives, we can't really figure out, well, what's the slope of the tangent line? Well, there's two slopes. There's a slope up here where the tangent line crosses 3, 4, and there's a slope down here where the tangent line crosses 3, negative 4. And so those two slopes, the slopes of those two tangent lines will have different slopes. That was redundant. Those tangent lines will have different slope values. One's positive, one's negative, right? And so what we're going to do to derive this thing is use implicit differentiation. With implicit differentiation, we do not need to solve an equation for y in terms of x. This consists of treating every letter, every variable, as a chain rule. So if x is in a term and we differentiate it, we treat it as a chain rule. If y is in there, we treat that as a chain rule. Okay, so here's what that looks like. If I take the derivative, if I do implicit differentiation with this equation, I take the derivative of the left side, so d dx of x squared plus y squared. And I set it equal to the derivative of the right side, so d dx of 25. Well, on the right side, the derivative of 25, that's just 0. The derivative of any constant is 0. On the left side, if I take the derivative of x squared plus y squared, I can take the derivative of each term separately. And since we're doing implicit differentiation, we're treating each letter as a chain rule. So x squared is if we think of it as a composite function, the square is the outer function and the x is the inner function. So I'm going to derive this with power rule. So 2 times the outside or the inside function, so 2 times x, times the derivative of the inside function. So the derivative of x we could write like this. The derivative of x with respect to x. And we say with respect to x because that's what we did in the beginning. Find the derivative of y with respect to x. So we're going to keep that consistent. So 2x dx over dx, or 2x times the derivative of x with respect to x. Okay, and then we're going to add it to the derivative of y squared with respect to x. So again, we're treating this as power chain rule. The derivative of the outside, 2 times of the inside function, so 2 times y, and then multiply that by the derivative of the inside function. So if the inside function is y, then the derivative of y would be dy with respect to x, or derivative of y with respect to x. So we have 2x times dx dx plus 2y times dy dx equals 0. All right, so dx dx, well, as x changes, so does x. So this basically equals 1. So this washes out. So 2x times 1 is just 2x. The second term, we have 2y times dy dx equals, so we have 2x plus 2y dy dx equals 0. We got rid of the dx dx. So now here we have an equation that has dy dx in it. We are trying to find dy dx. Here it is. So all we have to do is treat this symbol as a variable that we're trying to solve for. So if we try to solve for dy dx in this equation, first we're going to subtract 2x from each side of the equation, and then we're going to divide both sides by 2y, because 2y times dy dx divided by 2y is just dy dx. So we get dy dx equals negative 2x divided by 2y. And if we simplify that fraction, we get dy dx equals negative x over y. So here you have it. We used implicit differentiation to derive this equation, and it is equal to negative x over y. So let's talk about what this answer negative x over y means. This is the derivative of our equation. What does it mean on our graph? Okay, so if I try to find, okay, what's the slope of the tangent line of this equation at 4 different points? 3, 4, 3, negative 4, negative 3, 4, and negative 3, negative 4. So here's some notation around that. So the derivative of our function y with respect to x at this point right here. So you can think of this line kind of maybe represents our tangent line. So slope of this tangent line. We're going to take 3 and 4 as our x values and plug them into our derivative equation. So at 3, 4 will be negative 3 over 4. So 3 goes in for x, 4 goes in for y. We get negative 3/4. So then on our graph, the point 3, 4 is right here, and the slope of this tangent line that touches our graph at 3, 4, the slope of this line is going to be negative 3/4. At 3, negative 4, well, we're going to put 3 in for x and negative 4 in for y into our derivative equation. So we get negative 3 over negative 4, which is going to be positive 3 over 4 when we cancel the negatives out. So on our graph at 3, negative 4, that's down here, the slope of this tangent line is going to be positive 3 over 4. Now the next line, negative 3, 4 is this point up here on our circle. Our tangent line is going to be negative 3 over 4, which is just positive 3 over 4. And that's kind of intuitive, right? Because we know this is a positive slope line, so we should get a positive derivative answer. So that kind of matches up. Our last point, negative 3, negative 4, is down here in the bottom in quadrant 3. It's going to have a negative slope, very clearly from the graph. The tangent line has a negative slope. When we plug in negative 3 and negative 4 into our equation, we get negative 3 over negative 4. Well, those three negatives are going to make the whole thing stay negative. So we have negative 3/4. Okay, and that kind of unpacks what our derivative answer means when we do implicit differentiation. So let's look at one more example like this. Right here. Okay, so here's another equation. It's kind of a wonky one. I think it's kind of fun. If we practice doing implicit differentiation, we're going to take the derivative of the left side and set it equal to the derivative of the right side of the equation. Okay, and so the derivative of x cubed plus the derivative of y cubed. Those are power rules, and there's a chain rule, because remember, we're treating each variable like it's a chain rule. So x is the inner function, y is the inner function. The derivative of x to the power of 3 is 3x squared times dx dx, which just cancels out. And we're going to add it to the derivative of y cubed, which is 3y squared, times the derivative of the inside function, so dy dx. And that's going to be 3x squared plus 3y squared dy dx. And this is equal to the derivative of the right side. And so notice we have a 6x times y. So x times y means we have a product of functions. So we're going to have to use the product rule to derive this thing. So the product rule is the first function times the derivative of the second function. So 6x times the derivative of y with respect to x. And we're going to add it to the second function times the derivative of the first function. Well, the derivative of 6x is 6 times the derivative of x with respect to x times y. Okay, and then dx dx cancels out here. So on the right we have 6x dy dx plus 6y. On the left we have 3x squared plus 3y squared times dy dx. So our whole equation, we have two terms on the left, we have two terms on the right. Each side has one term with a dy dx factor. So what we're going to do is we're going to move this dy dx terms on the left. We're going to move the other terms, the 3x squared, over to the right. And then we're going to factor the dy dx out of these two terms. So we have 3y squared minus 6x. That's all times dy dx. It's going to be equal to our 6y that remains minus the 3x squared that remains. Okay, and so the last step we're going to do is we're just going to divide both sides of our equation by 3y squared minus 6x. And that will isolate dy dx. So dy dx is equal to 6y minus 3x squared divided by 3y squared minus 6x. Okay, so let's take that function and let's apply it and connect it to our understanding of the graph. So we'll take dy dx as defined right here. Okay, here we go. Let's see here. I think in class the graph didn't work, and now it is working. So let's see if we can get rid of one of those graphs real quick. Let's delete that. Alright, so this is how we did it in class. So I want to find the derivative of this thing at the point 3, 3. Okay, if you're at school right now, if you can hear, I got the intercom going on. So we'll ignore Mr. Nagtal. I'm probably supposed to be in a meeting or something. Okay, so if we find the derivative of this equation at the point 3, 3, this blue line is what our original function looks like. X cubed plus y cubed equals 6xy. That looks like this blue line right here. It's got this little loop-de-loop. And so the derivative at 3, 3, 3, 3 is right here. The derivative is the slope of our tangent line. And again, notice we can't derive this normally because at x equals 3, there's 3 different y values that we can get. So specifically at the point 3, 3, the tangent line, we're going to take 3 and 3 and plug it in for x and y. Everywhere there's an x and a y in our derivative equation. So we'll get 6 times 3 minus 3 times 3 squared divided by 3 times 3 squared minus 6 times 3. Do some calculations. So the derivative at 3, 3 is equal to negative 1. So the slope of our tangent line of this curve at the point 3, 3, well, the slope of that tangent line is negative 1. Alright, so our homework for this lesson, really I want you to practice doing a little bit of implicit differentiation, but I also want you to practice using with what variable we're taking the derivative with respect to. So some of the examples have y and x as the input and output. Most of them don't. So really have to pay attention to what we're taking derivative with respect to. So in this case it's dx, so with respect to x. You really have to pay attention because this won't always be x in this lesson. So we're really testing our ability to keep our letters straight. My joke in class was kind of like we've been so trained to be comfortable with x and y. It's like our security blanket, and now we're taking away your security blanket. I'm sorry, the struggle is good for you. maybe eat a bar of chocolate or something to make yourself feel better. Okay, so if I take the derivative of this equation with respect to x, I want to find it in terms of x only. Currently this equation or this expression has a y in there, so I'm going to want to get rid of this y after I derive it. Y is defined as 3x to the power of 3 plus 4. So I can really quickly derive y. It's going to be 9x squared. Alright, so I have those on my back pocket. I'm just going to keep them there for a minute. So derivative with respect to x of this expression, if I use implicit differentiation, I'm going to take the derivative of 2x squared is going to be 4x. And at this point, we're just going to assume, this is a chain rule, so the derivative of the inside function would be dx dx. I'm not going to write dx dx, so we're just going to know that whatever function we're taking the derivative with respect to, we don't need to do that step. It's kind of redundant or repetitive at this point. So that's 4x. The derivative of this one, we've got some chain rule going on here. So the derivative of 2 sine of y is going to be 2 cosine of y times the derivative of the inside function y. So times dy dx. So now I have the equation derived, but it says in terms of only x. So I need to replace y, and I need to replace dy dx. Well, we have those in our back pocket. So I'm going to replace y with 3x cubed plus 4, and I'm going to replace dy dx with 9x squared. And if I do that, then I now have a new expression only in terms of x. Okay, here's one more example. Like I said, security blanket gone. X, y, not in this problem. Rely on your understanding of what we're learning about with implicit differentiation and derivatives in general. So w is defined right here in terms of u. We can use power rule to find dw du, or the derivative of w with respect to u. No longer x here. I know, shocking. Alright, so now if we do implicit differentiation with this expression in terms of y or w and u, we can get power rule here, so 4w to the power of 3 times the derivative of the inside function. And remember, it's with respect to u, so the derivative of the inside function is dw with respect to u, minus the derivative of 2 sine of u is going to be 2 cosine of u. And then since we're doing with respect to u, I'm not going to write du. Alright, so we've implied this with implicit differentiation. I'm now going to write it in terms of only u. So w gets replaced with our u function or expression, 3u to the power of 5 plus 1. dw du gets replaced with our derivative of w, 15u to the power of 4. And we now have our expression in terms of only u. Yes, we could simplify this a little bit, but this is calculus. We're not going to do the algebra simplification. That's it. Alright, so takeaways. We can now use implicit differentiation. Hopefully we have a little bit of understanding of what's going on when we talk about implicit differentiation. Basically, finding the slope of a tangent line at a given point, not just at a given x value. Also, we're treating every variable like it's chain rule. And this is complicated stuff, so just take a moment to realize most of the world could not understand the last 5 minutes of this video. I mean, they could, but for whatever reason they're not going to have the opportunity to learn this and understand it. But you do have that opportunity. So this is where math becomes so complicated that most people in the world won't have the opportunity to understand it. So to the rest of the world, when you do stuff like this, it just looks like magic. So for that reason, welcome to Hogwarts.